within a few seconds.
Okay, good. So I have a short introduction. So let me share the screen. I hope you all can see the screen.
Yes.
Okay, good. So this is the second session on site and infrastructure. We also had it yesterday morning. This was the program for yesterday. This is for today. And you see it's partly still about the source and Atos site, but also partly about the site in Belgium, Germany, and the Netherlands. And then some experience from Kagera and also CERN. So I think it's very good that we have two sites. So yesterday you had 7 talks or so about source and Atos, and I think it's great to have two sites at this moment because we can learn from each other. So today you will hear about the other one. So that is in this border area between Belgium, Germany, and the Netherlands, and there are quite some institutes, scientific institutes, that are interested in this site and working on it. I think many of the things that we're doing are driven to get good low frequency sensitivity. And if you look at the low frequency sensitivity of the current instruments, it is shown over here, LIGO and Virgo, you see they're about the same, while they have different strategies. But still, they're not a design value. So if you want to go to design value, then for Virgo, it means about 2 orders of magnitude that we still need to improve. And then we are where we want to be at 10 Hertz. But if you want to go to Einstein telescope, it is another at least 2 orders of magnitude. So that is what is driving us underground, doing cryogenics and the cancellation or the subtraction of gravity gradient noise. So the challenge is huge to do this. And the way we have decided to counter this in ET at the moment, the baseline, is of course the super attenuator. So this drives now the height of many caverns, 30-meter high caverns. These caverns are huge. So if in any way we could think about doing something more compact there, that would have a tremendous impact on the infrastructure. And the other thing that you can think about if you listen to these talks is on the vacuum system. So here you see the Kagera detector. So that is a 6-kilometer vacuum system, 1 kilometer underground. And you see the environment is not very friendly there. If you look at Einstein telescope, then with 130 kilometers of vacuum, it is a volume of 120,000 cubic meter, more than 400,000 square meters, and at a pressure around minus 10 millibar. So if you compare it to the CERN vacuum system, even if you include cryomagnet insulation and distribution lines, still this is a huge vacuum system. So there are also possibilities for cost savings. One is well known. It came from the discussions also in the US last year for Cosmic Explorer, that is using mild steel. So there are certain industries in Europe that we could involve there and look at this potential cost savings. So we will talk more about it at the end of the session this morning. And there are other ways to do this. So these will be things that would have a big impact on the infrastructure. And then if you realize that the infrastructure and the vacuum system together is 85% of the cost of Einstein telescope, I think there is now a window of opportunity for us to do some R&D with the focus, maybe to achieve some cost savings. So that window of opportunity is now until we start installing in 2026. And the takeaway that I would have on this session yesterday and today is that hopefully this could also lead to some defined R&D, and even better if we can do this in a global effort, for example, together with CERN and Cosmic Explorer. So this as background. Maybe right now we should start with the first talk, and that first talk is by Luciano Enrico. Luciano, are you there?
Yes, I'm here.
Maybe you can share the screen.
Yes. Do you see the screen?
Yes.
So, okay. Second. So, good morning to everyone. I am Luciano Enrico. I'm a PhD student from University of Napoli. I'm also a member of Archimedes collaboration, which is an experiment of fundamental physics. I will quickly describe next slide. Today I want to report our first measurements in Sosenatos because of their impact on site characterization. I will explain it deeply in 1 minute. Now, what is Archimedes? So, in few words, it's an experiment aimed to investigate if a quantum vacuum of electromagnetic field does interact with gravity or not. This is an open question in fundamental physics. I unfortunately have no time to go into the details now, but anyway, this interaction should reveal a very important link between quantum mechanics and gravity. And Archimedes is the first and maybe the only experiment up to now aimed to answer it. Concretely, Archimedes will use a sample, a crystal made of YBCO, and a super-sensitive beam balance to measure weight fluctuations inside the sample induced by modulating vacuum energy stored inside the sample. This sensitive balance, very sensitive balance, is the reason why Archimedes can bring some benefits to ET studies. In fact, we already have a working prototype of this balance, which can be used as tilt meters as well, measuring directly tilt noise in Sosenatos. Moreover, due to its good sensitivity, this tilt meter can also be used to contribute to Newtonian noise cancellation studies. And finally, in general, since Archimedes' experiment will be entirely performed in Sosenatos because it requires a site with a very low seismic noise, this experiment can also be a quality check of general quality check of the site that will host a full experiment. So let me go to describe the balance in this moment. So the balance, very simply, is composed by an arm, a small arm, 50 centimeter long, very light with a low moment of inertia. This arm is suspended through thin joints, a design very similar to LIGO tilt meters. Then these joints are bolted to the ground through some heavy pillars. The balance, this arm have a center of mass that can repositioned finally, and it's brought as close as possible to the bending point of the joints, around 10 micrometers of distance. And in these conditions, the resonant frequency of this arm is around 20-30 millihertz. So this arm is free to move, and its tilts are read by an optical readout, which is a Michelson interferometer entirely built up to the suspended arm. Here in the picture, you can see the red beam that is the laser beam passing through the interferometer. There is also a second optical readout, which is an optical lever below the suspended arm, which is just used as coarse positioning. Regards to the interferometer, it's not just a basic Michelson interferometer, because it's equipped with the prisms and lenses to answer to different purposes. Now I will go into the details. Prisms are placed below the beam splitter, so you can see that there is the injection, the collimator on the left. The laser will go through the beam splitter. The beam will be split in two paths. One path should be shorter than the other by design, but we added this set of 4 prisms below the beam splitter in order to equalize the length of the 2 paths. In this way, we suppress highly the frequency noise that we should measure at the output of the interferometer. Now the difference between the 2 paths is reduced to a couple of millimeters at best. Speaking of laser noise, we also have a suppression of the amplitude noise, because we measure independently the peak off of the input to laser beam, and we then normalize the output of the interferometer to this peak off. Then we have also the lenses, as I said. The lenses are placed below the beam splitter and below the inclined mirror, always up to the suspended arm, in order to maintain a good alignment and a good contrast against static tilt. In this picture, you can see very easily how lenses works. So you can see that even if the suspended arm below is tilted, the interferometer should misalign, but thanks to the lenses, this misalignment is at the second order in the angle. But also, thanks to the lenses, just moving vertically the input laser beam, we can recover completely the alignment and the contrast. And I want to stress that the entire realignment can be done without moving optical parts on the suspended arm. So the entire arm is always kept free and not controlled, because there is thanks to the lenses there is no need to do that. After that, we of course have a suspended arm free to move, and in fact it will move because there will be environmental noise moving it. So we also have a feedback control to keep it always into the same configuration, in the same position, which is the position around it we want to work. And in order to do this, we have, of course, a digital filter and an actuation system. Now, we used as a control system a National Instrument system. You can see it on the picture below. And as an actuating system, we use the electrostatic actuators, which is simply 2 couple of metallic plates that we charge. And as you can see from the mirror, these plates from the picture, these plates are the blue one in the picture. Charging them, you can induce a force on the suspended arm, and by electrostaticity, you can drive the suspended arm. So this is the system, and the system, as I presented it, has been brought firstly into Virgo site, in particular at North End building, and we had it doing measurements from April to mid-July of the last year, which is during the first phase of O3. In that occasion, we actually had no peak off, so we had a higher amplitude noise, and no prisms, so no equal arms, which means a higher frequency noise. Nonetheless, we did the measurements that I'm showing in the graph on the right, in the frequency band of the Newtonian noise studies. And results are encouraging because if you compare these results with the ones in LIGO, you can see that are actually comparable. There are some ranges, 1030 Hertz and 1820, where the floor is comparable with LIGO. And in other ranges, the noise is higher, but I mean, we are measuring seismic noise here. So it's not, the sensor, this is not sensing noise. This is just a physical measurement. We are measuring the tilt in Virgo. Then we moved the entire sensor and we upgraded it because we added the prisms and peak off in Sargrav. And I'm happy to say that Sargrav is an operational site. We are already taking measurements as an almost full experiment in Sargrav. So we have a laboratory, we had acquisition, we have pumps, optics, and stuff like that. So I'm happy to say that you can work in already work in Sargrav. And here I'll show you these first results that are very encouraging, because as you can see, in the same frequency band that I'm shown in Virgo, we reached this sensitivity. So here we are touching, we are going down nanoradians over square root of Hertz. Around 9 Hertz, we gone up to 6 times 10 to the minus 13 radians over square root of Hertz. I repeat, this is a measurement at closed loop after
3 more minutes.
Yeah, after 1 night of data. So it's a very robust measurement. And as you can see, we went a couple of orders of magnitude, even better sometimes, respect to Virgo. And again, we are sure that we are limited by sensing noise. We are not still touching the seismic noise in Sosenatos. So at conclusion, we can say that our tiltmeter has shown the best sensitivity in the world in the region 2 Hz to 20 Hz in Sosenatos. At our knowledge, Sosenatos has shown the lowest tilt noise ever measured. We found no publications reporting sites with better seismic noise. And these results are also encouraging for the Archimedes experiment as well, because now we are very motivated to start our studies in the region to lower frequencies, 1 milliards to 100 milliards, which are more interesting for our experiment. The further developments will be a commissioning on diffused light, because at higher frequencies we have a diffused light noise. We want to do longer measurements, campaigns for site characterization, day, night, other seasons, and stuff like that. Then we want to start a coherent studies with the seismometers. And of course, as I said, we want to start also measurements at lower frequencies, maybe also using a heavier suspended arm, which is what we want to do for the Archimedes experiment. Thank you, I finished.
Thank you. This is a really good result. So I think Peter had a question.
Yes, do you hear me?
Yes.
So, Luciano, I would like to ask, how do you insulate, I mean, what kind of environmental effects do you measure now, and what are the most important ones that could influence, in spite of the various insulation policies, the measurement?
I'm sorry, what do you mean by isolation?
I mean, you don't want to measure pressure, for example, or temperature, but you measure seismic noise, and somehow, so what are you exactly register here?
Okay, so I mean, the entire measurement is performed keeping the system in vacuum. up to now, we are not isolating the entire vacuum chamber from temperature, but in any case, we expect that the noise induced by temperature fluctuations is a noise affecting another frequency region, so lower frequency regions. In this frequency region, we see some structures which are targeted. We know that these targets, those structures are, for example, the resonant frequency of the vacuum chamber, or that is inducing a noise through diffused light and stuff like that. So in some sense, we know now that we are already touching the seismic noise. And we also have we are starting to build a noise budget in this frequency region. So we know that in this, this sensitivity is limited by sensing noise, because we calculated it, and we know that it should be in this to this level. So we are quite sure that we are not measuring other kind of environmental noise in this way.
And a particular question, whether you will be able to measure gravity gradient noise directly?
Well, we don't think that our sensor is directly able to measure gravity gradient. Otherwise, let me say that if you are able to do that, you should see also, for example, gravitational waves directly, because if you are able to see how the gradient, the gravity is moving, also when a gravitational wave will pass, you should see a signal. So we will just measure at our best the seismic noise.
But it is not exactly the question. If you pass by the device, you can measure that. How far? I mean, you as a person, as a gravity created, I mean, mass point.
I mean, we still have to, in some way, we still have to quantify the effect of people moving around the vacuum chamber, and the effect of the gravity of people moving around the chamber. But in any case, when we do this kind of measurements, the sensor is left alone. I mean, there is nothing moving around it in a radius of at least 100 meters. So I don't.
Sorry, there is another question by Thomas, but can it be short, and also the short answer?
Yeah. Can be.
Yeah, okay. That's I'm ready. Thank you very much, Luciano.
Okay, so in your spectra, there are these features at 7 and 17 hertz. I wonder, that are similar between the two sides. I wonder if you have any idea where they come from?
Yeah, more or less, because at 7 hertz, there should be the resonant frequency of the vacuum chamber, one of them. Then this feature at 17 hertz, it's still under studies. Also because actually we never reached this so low sensitivity, so good sensitivity. So these peaks are still under commissioning. Another thing that we want to care better is, for example, the anti-aliasing filters that we want to, because now, I mean, the sensitivity is so good that we would like to take care also very, very carefully also about these details, because we are afraid that there could be an aliasing noise coming through. But
Luciano, I'm sorry, but we need to carry on.
Yeah.
Thanks a lot. Okay. So thanks. So we should continue. I think the next speaker is Thomas Bulek. And he will show us more about seismic noise in Sosenatos.
Okay, let me share my screen. Share and show. Okay. Can you see this?
Yes.
Okay, so in this talk, I want to summarize on the project of investigating seismic noise at Sosenatos and also other ED candidate sites, but I will not talk a lot about the other sites. And this project is a collaboration of many people listed here, and also, of course, we have to thank the Sosenatos team and especially Luca Lodo for lots of help during this work. So the project started a couple of years with the Aspera funding, and we aimed at designing and building low-cost seismic sensors to make them work in a time-synchronized way and deploy them at candidate sites and gather as much data as possible to characterize and compare the sites. But now I'm concentrating on a single site, the Sosenatos site. So the sensor that we used was based on 2.5 Hertz geophones with custom electronics connected in series for data acquisition and for time synchronization. We could gather data to either a central computer, but also to store it on SD cards in case the communication failed or if we wanted to use standalone sensors. So here is a picture of the sensors that we have used. So on the left-hand side, you see the geophone with preamplifier and then the sensor box, and the three sensors for the XYZ axis are beneath the data acquisition board. It's all placed into a watertight box and which is placed on a heavy metal plate to install it somewhere deep in a potential site. The sensitivity estimates that we have measured, these are the noise levels for the sensors. They are so we tried the 4.5 Hertz and 2.5 Hertz sensors, and above the resonant frequency of the sensors, we have the sensitivity at about 10 to minus 10 meters per second per root hertz, which is well below the noise level we expect underground. And recently we have also checked the uniformity of the sensors, whether the gain sensors of the sensors is similar by cross-calibrating the sensors with a Trillium 120 that was placed in the basement of our institute in Warsaw. And here we see that the sensors behave pretty uniformly in the window of the highest sensitivity. So let me now go to the Sosenatos mine. These are the pictures that we have already seen in many presentations yesterday. So we have installed a network of 7 sensors underground, and you can recall the map. This is the the ramp where you enter the station, the mine. Then the first 3 seismometers are along this arm, and then we had 4 seismometers up to up to here. And the typical distances between the seismometers are of the order of 50 to 80 meters, maybe to 100 meters to 230 meters, as I see it now. Yes. So that was the network. When it worked, we acquired about more than 4,000 hours of data, and we also had 1 seismometer on the ground from which we acquired nearly 1,600 hours of data. It was installed later. For comparison, we also had 3 other sites in Poland, Hungary, and Spain with different amounts of data and different numbers of seismometer. So Regarding the data analysis, we decided to concentrate on the initial data analysis with the seismic spectra, then with the daily variability, and then with glitchiness or quake, microquake analysis. And with this in mind, we started working on the sensors. So here you see, so we had 7 sensors, 3 axes each. So we essentially had 21 separate data streams and 1 sensor on the surface with 3 data streams for XYZ. So that means quite a lot of data. So for the visualization of this data, I decided to plot the spectral densities of the amplitude acceleration spectra. So this is in meters per second square per root hertz. And we present this density maps of the spectra, where we plot the density of occurrence of spectra as a function of the frequency. So, and this is in the Newtonian noise band from 2 to 30 hertz. So the dashed line on the bottom of the plots is the Patterson seismic noise model. And already here you see that, okay, the left plot shows the vertical spectrum, and that's for the Z4. For the fourth sensor, the right-hand side shows the Y direction spectrum for the same sensor. So one thing that you can already notice is that around a few hertz, the seismic noise touches on the Patterson low noise model, but there is some variability with a prevalent structure peaking at around 15 hertz in both directions. If we look at the vertical spectra for the other sensors, there is one thing to notice, that the spectra are actually in some sense similar, but that they are different, that the seismic noise varies on the scale of about 100 meters. And you can also see that for some sensors, we see lines, which are probably the seismic disturbances due to some machines working nearby, pumps or other things that happen there. But if you look at the sensor that is the farthest and the deepest in the mine, the sensitivity, so the lower right graph, this variability is lowest and the influence is becoming smaller. For the vertical, for the horizontal spectra around the x-axis here, we see that there is also variability which is seen, and for this fifth sensor, which was full of disturbances in the vertical direction, the horizontal disturbances are also quite significantly present. For comparison, we can also look at the surface spectra, which are here, and they are, of course, slightly higher. They are a factor of 2 to 3 on the average higher than the underground spectra. There is much larger variability, but still these surface spectra are on the quite low side. So this is the minimum here is quite low. If you look at the time, okay, how the spectra vary with time. So here we have these spectra, and you see that here the animation of how the spectrum moves up and down with the with time, and so the front plot is for the 7th detector, So you see that at night, where when the touching on the low noise model. If you look, okay, so here is
5 minutes.
Okay, so here is the daily variability underground, and then okay, let me go to the surface. So at the surface, of course, this goes much higher, and we see a little bit of a different variability. So we followed this with the earthquake analysis, and in the earthquake analysis, we divided the data into 1 second pieces, and we looked for the maxima in the 3D velocity for each segment. So we defined an earthquake as a segment with the maximum of above 0.5 micrometer per second velocity, and an earthquake duration as a set of such segments followed, before which we had at least 1 minute of quiet time, and which was followed by yet another minute of quiet time. So we then created or calculated the list of quake events in our data stream, and we analyzed this data stream and their frequency. So here is the estimated of number per year as a function of the peak velocity in meters per second. So you see here that there is quite some very low quakes, and they really vary from one sensor to another. Then there is another peak of about 10 to minus 5 meters per second with nothing above that. And this 10 to minus 5 amplitude per second are happening around at the rate of about a few hundred. So this is like 2 per day. So this means that the glitchiness of the data over there and the microquake rate is pretty low. Other lessons learned from the whole experiment is that the conditions underground are at some places quite challenging. There is humidity, there is some chemistry, and this is how a sensor looked after an extended stay underground. And the second consideration that we had to take into account is that in one of our connector boxes, we had a visit of life forms from the surface, who went a few hundred meters underground and feasted on our cables. So I think that that's a consideration for construction of the Einstein telescope, to really think how to get rid of such unwanted guests. So in summary, we found that seismic noise is really low. The glitchiness is smaller than other sites, and I haven't shown the comparison with other sites, but the seismic noise is the lowest from all the sites we have investigated. We are planning in the next step to do the correlation analysis between the sensor, to study the Patterson model and the noise floor. We think of putting a smaller underground Newtonian noise testing array to gather the data for Newtonian noise characterization, and also to put another project is to put a network of infrasound microphones to do the infrasound field characterization underground. And with the project that is developing here in Poland, we can provide many inexpensive seismic sensors, and we can provide several infrasound microphones, because we have designed a new infrasound microphone, which is quite less expensive than the commercial ones, and it has quite a good sensitivity in the Newtonian noise range. Thank you.
Okay, thank you. Are there any questions?
Hello, can you hear me?
Yes.
Hi, Tomic. So I have a question, like how do you calibrate the sensors? Because the last time I had a talk with you, we had a discussion about the calibration.
Yeah, so the first calibration, as you know, was done in NICHEV, and that was the work done on this vibrating table, and then we found the noise level in the seismically isolated table. And then in Warsaw, we have placed the sensors on a relatively quiet place in the basement of one of our buildings with a Trillium side by side. And we did the data stream comparison between the two to find the gain as a function of frequency in relation to the gain that we knew, to the signal that we knew that was measured by a well-calibrated sensor.
There was another question about the information on the noise below 2 Hertz. Can you say something about that?
Is it in the chat window? Or?
It's in the chat window, right? Yes.
Okay, so let me stop sharing so that I can access the chat window. Well, we don't have much information about the noise below 2 Hertz. We have some sensitivity over there, but as you see, we use the 2.5 Hertz geophone, so the sensitivity drops. So I think that we could find something, but that's not going to be as reliable as the work that is done with more sensitive broadband seismometers. The aim of this project was to look at the 2 to 30 Hertz noise. Okay.
And you also mentioned the infrasound measurements. Can you say more about it? How far are these plans?
At Astrocent, which is a new institute in Warsaw that also we have developed an infrasound microphone with the similar idea as with the seismometers we had. So we want to have an inexpensive sensor that will be sensitive in the Newtonian noise band, not the broadband. And the advantage will be that the price of the sensor will be much lower than the commercial. So now our prototype is a microphone that is sensitive from 2 to 30 Hertz with the sensitivity of about 10 to minus 4 Pascal per root Hertz in this band, and the cost is about €100. So we can build several tens of such or even 100 of such sensors and put a network to be able to characterize infrasound fields underground. So one of the projects that we have is to first try it at a test site in Poland, but then to go on and install something like that in Sardinia, of course, in cooperation and in agreement with the with other Sardinia site testing activities.
Yeah, but also yesterday it was presented that there is an array of, I think, 15 sensors to look at the ambient noise on the surface. Are your sensors also participating in that study?
No.
Okay.
Not yet.
Good. I think there are no more questions, so thanks, Thomas, again. Let's continue with Fred Nguyen, who will talk about Etest. Fred, can you share the screen?
Yeah, I'm doing this now. Just let me know if it works.
Yeah, okay.
And do you see the slides?
Yeah, okay, now it's fine, yes.
Okay, great. Hi, everyone. So my name is Fred Nguyen. I'm from the University of Liège, and I will be presenting today on behalf of the project consortium, which is called Etest, which basically aims at studying the ET Eurasia, that is between the region between the Meuse and the Rhine. So that Jo presented earlier at the cross point between Belgium, the Netherlands, and Germany. And I will be speaking about the general objective, some geological condition, and some plans we have for hydrogeophysical imaging. So there are a lot of people here on the team, so I hope I did not forget too many of them here. So the main partners which are involved in the, I would say, subsurface part. So Etest is basically handling two parts, one dedicated to a prototype led by Christophe Collet, and another part which looks at the subsurface, where the main players would be Liège University, University of Bonn, Aachen University, KNMI, and NICEF as well. So the outline of the talk is I'm going to be looking at overall project objective, discussing the site perimeter. So you see here where the site is located. So we've seen that before at the triple border point. And you see one possible area here where we could have a corner. You see it's quite, despite some urbanization nearby, it's quite quiet. I will be talking about key geological condition, the need to actually have imaging at that depth, and then present a little bit on the hydrogeophysics and groundwater model, and insist on the future timeline. So the project basically aims at acquiring new data and gathering existing database in the region to produce basically different models. And the final deliverables, I would say, is to have a ET design in the EMR region. So the database consists basically, there are former seismic data, which are actually reach deeper than 200 to 300 meter depth. So they don't have too much detailed information at those depths. And we'll be gathering new geological data using boreholes. We'll be gathering geophysical data, performing geomechanical tests, and also hydraulic tests. Basically, those data are then going to be used to build underground models, and you can see basically three scopes of those. One would be engineering geology, another one would be groundwater, and the other one would be seismic noise. So the project started in January 2020 and will last until July 2023. So the site perimeter, so you see here a most close-up look at the region. So the Netherlands here, Germany is here, and Belgium is here, and you see here in pink the residential and some industrial areas nearby, and you see that in the middle you have this quiet area where you have those Natura 2000 sites, which are preserved sites where you have basically no activities, and some of the work that I'll be showing will be focusing in those areas. So some of the key geological condition in the area is that I would say compared to Sardinia, we basically have the hard rock, which is found at some depth, and above this hard rock, we have some soft rock that allow us to basically dampen here the ambient noise, for example, that you may found from wind turbines, and we have some host rock, hard rock that allow us to host the subsurface caverns that are harder rocks. And also we have the risk in the area to have some limestone formation. Yeah, so we have some limestone that we have the risk to have in some faults, some karsts, some solution. So in terms of structural geology, what we've gathered so far is you have this older Paleozoic bedrock that is actually highly folded due to former tectonics and faulted. So you have two types of faults. You have normal faults, which are the most critical one because those can have water-bearing faults, and you have thrust faults that deform the structure. So this is basically what you see here in purple and in blue, and that's where you have the Nguyen formation. That's where they used to mine the coal, and below that you have the stronger Famenia formation, which actually is the one we are actually targeting at. And above those rocks, you have basically younger sediments, which are basically chalk and Cretaceous units. And then this is the soft rock that I was talking about. So we're going to build up a structural geology model, basically based on geophysics, including basically also the uncertainty. So we've been doing that using Gempi, developed by the team in Aachen. You see here an example of the 3D model that can actually be produced. In terms of lithology, so the type of rock that we will find, as I said, the top rocks are basically weakly lithified. So there are sands, there are also clays, and there are basically chalks. And so those ones are the one that we call the dampening rock. And the Paleozoic rocks, basically you have mainly limestones where you have this risk of karst, and then we have those upper Devonian rocks, which are basically the shales, the quartzitic sandstone, the quartzites, which are really hard rocks where we can sit actually the big caverns. One of the trick in the area, you see here a former geography during geological times, is that you might have some erosion that actually erodes some stratigraphic units, and so you might actually miss in some of the geological stages in the study area. So some of the critical points, and this will be addressed by a talk by Florian Amann later on, is that at the top, as I said, you have the chalk, so you have those younger rocks, which are important for dampening, but they also have, they all can cause an issue in terms of basically building the access shaft and also the drilling stability or groundwater issues.
Yeah,
and below that, 5 minutes, I have to speed up. The limestone poses karstification issues, and then we have to find the suitable rocks for the caverns. So because of this complexity and because you have many variations laterally and vertically, there's a need for geophysical imaging to basically identify the different strata. And so this is basically what we plan to do for seismic reflection lines, to basically try to map the geological unique boundaries and the relevant faults. And this will be included in a geological model. In addition to that, we perform different multi-method surveys. So this is more near surface geophysics at the site where we actually plan to drill here. This is CATSM to basically identify those shallow layers, the potential karstic area, and also to map shallow faults, an example of seismic refraction studies, and an example of ERT. We also have a seismic parameter or seismic noise quantification with measurements at single and multiple station. And I think there is a talk by Sumin Kali, which we just heard asking a question, and also Florian later on that will address this. This is some work also performed by one of our team in the area. Sorry, you have to speed things up. In terms of the groundwater model, well, we know that the groundwater condition is going to be a key factor for actually installing any underground project. That's what we heard also yesterday with the CERN experience. And we know it's controlled by the discontinuities that you can find in the rock. So it's quite important to understand how groundwater flow in the subsurface to have a good basis for the design of the Einstein telescope. In addition, in the area, you see here that you have a lot of abstraction of water for usage, mainly the shallow water.
I screwed up,
Okay.
7 more minutes, sorry.
Oh, 7 more minutes, okay, so I can slow it down a bit more. And so the groundwater abstraction here is, you can use it, for example, for shallow geothermy, low temperature geothermy, but also be used for environmental impact assessments. And so the idea is to build up this cross-border EMR groundwater model that is going to be not only useful for the Einstein telescope if the site was chosen, for example, but also for the population later on. We're going to be building a hydrogeophysical observatory in the area and monitoring public database. So we are in the phase of identifying actually a site to host this underground R&D lab, which is basically to install different type of sensors, so electrical, hydraulic, and seismic sensor to monitor the subsurface. So not only the seismic noise part, but also to perform at that location hydraulic tests that we will monitor using geophysical imaging. So this will allow us to have this 1:1 scale experiments to be able to calibrate or validate the groundwater model that we actually will develop in the area. So as I said, the project started in January 2020, and then we had, of course, the COVID issues, so we are a bit delayed. But the future timeline, you can follow our activities on the test site, on the website, sorry, not the test site that is indicated here. So we will have, starting actually in a week or so, the seismic vibration campaigns near the wind farms, and also to look at the effect of the faults on the seismic noise distribution. We started tendering for drilling, testing, and putting the observatory. So hopefully works on that will start in February 2021. The seismic line will also be done next year, as well as the deep electrical tomography survey. So those are 3D tomography survey that will go about 500-meter depth to try to also map the geology, and particularly those karstic formation, together with seismic tomography, so active seismic. And what is ongoing is, of course, the modeling part on the 3D. the hydrogeological conceptual model, and also we have this GIS project that I think Florian will mention in his talk. And I think I'm at the end. I'm sorry if I rushed the talk, but I'm through. Thanks.
Thank you, Fred, and apologies for.
Yeah, no problem.
Okay, so are there any questions?
Yes, I have a question.
Shaman?
Yeah.
So I just wanted to know that if the data for the active seismic will be available to people with outside the Etest.
Yeah, it should be possible once, of course, it's gathered and first processed. One of the plans of the Etest project is to have this open database, and where basically the data gathered in the project is available outside of the consortium. Yeah.
Okay. Thanks.
Yeah, and that is true also for the models, not only from the database.
Yeah. I would like to ask which depth you plan to put this underground R&D lab.
This is going to be well. The lab is basically different setups of cross boreholes. So they would reach about I would say 300 meters, from 100 to 300. So it's not a cavern per se. At the first stage is going to be really monitoring cross borehole experiments where we can inject tracers, for example, and monitor basically using a geophysical imaging where they go, how fast they go, to basically calibrate the groundwater model.
Okay. Thank you.
Yeah.
I might have one more question actually.
Yeah, sure.
So how seriously are you considering putting a string of geophones down a borehole?
A what?
A string of geophones down a borehole. Like many geophones, like a VSP maybe.
Oh yeah. So now on these ones it's so either we have the sealed boreholes with the one seismometer, or we have basically the electrical sensors.
But so, for example, in the Etest you will have boreholes, right? Like new ones.
Yeah.
So how do you use them? Like, do you again put the same as Terziet, like one on the top, one on the bottom, or you don't?
Yeah.
Want to put
so those three would be similar to Terziet, and the other two for the observatory is going to be screened. So basically open. We need contact with the groundwater, and then we have so the sensor there are mainly hydraulic and electrodes.
Okay.
At this stage, yeah.
Then on the boreholes, will you measure over distances of 10 kilometers that we can see what the correlation is between the different end stations?
In terms of imaging, no, it's gonna. I mean, it depends what we measure. If you talk about the geophysical imaging, this is going to be only let's say 100 meters between the boreholes. But I'm not sure if you talk about that, if you refer more to the seismic correlation, for example.
No, seismic correlation, because
the
worry is that if you have these collocated interferometers, that you have common noise.
Yeah, then you can compare those three, for example, here.
Okay.
If you see, yeah. And then the observatories would be the one located. Sorry, I went a bit fast, but it would be the one located here.
Michele?
Yes, maybe you said and I lost it, but inside within this project, Etest, are you monitoring also the subsidence of the site? Because I believe that with this complex structure, this zone cannot suffer also by subsidence.
Yeah, so it's not directly aimed within the Etest project, but we work together with the geological surveys, and there've been some monitoring of the subsidence. But it's not within the. I mean, it's not within the project directly.
Okay, and I don't know. I'm not expert. Maybe you can answer. But you believe that the subsidence on the surface will be really different from the subsidence in the deep, hard rock, because you have a complex structure. So I think we need a model to correlate what we measure on the surface to what happens to under.
Yeah, I'm not sure actually I can answer that. I would have to go back to the works of Pierre-Yves Leclerc, who studies subsidence. I wouldn't expect it to be severe actually.
Okay.
Yeah.
I have another question. In the past, there was the construction of a high-speed train going to Liège and Aachen.
Yeah.
And how much experience is available from that project?
Well, we would need to reach out to the engineers, but I'm pretty sure the company would be willing to collaborate and provide information.
Mm-hmm.
So we do have contacts with people who are involved in the different tunneling project around the region.
Okay.
Yeah.
Good. If there are no more questions, I don't see any hands up. Sorry. Yes.
Sorry, Enrico Calloni.
Oh, Enrico. Yeah.
Hi. For what concerns the wave velocity of the seismic waves, I mean the speed of the seismic waves, we will have also some measurement of the speed of the sound of the seismic waves from the surface toward the hard rock. So in the path from the surface toward the hard rock.
Yeah, I'm not sure I understood clearly your question, but I think it was a question on the seismic velocity.
Yes, I am not an
so we started gathering some surface data from refraction data. I think Suman might actually show some of this data later on. So this is here. You have one example of the seismic tomography for the P wave velocity, which we only reach here maybe 60-meter depth, where we have 3,000 meters per second, and at those in the first type of rock that we encounter, but not yet reach the harder rock that it actually be underneath it. So we will need longer survey and deeper survey. So that I don't have the data to answer that yet.
Thank you.
And this is foreseen to this kind of measurement. Right.
Yeah.
Okay.
Yeah.
Schaumann in the next talk will show data on P and S wave velocities, and
exactly,
also on surface velocities.
Yeah, and also I guess the borehole will be doing geophysical logging or VSP to also get the vertical distribution of the velocities.
Right.
I mean directly sampled.
Yeah, so you will see that in the next talk.
Yeah.
Yeah. Any other questions? Good. Then
all right.
Thanks
a lot.
Yeah, thank you a lot.
Yeah.
And sorry for this upset.
No worries.
We filled the time anyway, but
yeah.
Let's have a short break of 10 minutes and be back at 10:15.
All right.